see you there. What's going on, fella?
Nothing, G. We just here straight chilling with this Atwood machine.
For real, Kev. What's it do, homie?
The purpose of this lab is to find the relationship between the theoretical and the actual values associated with an Atwood machine, namely the acceleration and the tension. In order to do this, two masses are selected, one of 0.1 kilograms and one of 0.2 kilograms. The theoretical calculations using Newton's second law, sigma F equal ma, are then performed to calculate the acceleration and the tension. Then, an actual Atwood machine is constructed, and using a video recorder and a meter stick, the actual acceleration and tension are found. To find these values, the kinematics equation that was used was delta y equals vi delta t plus 1/2 a delta t squared. The initial velocity, vi, was 0, so the vi delta t term is 0. So, the equation is rewritten as a equals 2 delta y over delta t squared. Then tension is again found using Newton's second law, sigma F equals ma. The results found were that the theoretical acceleration and tension were 3.27 meters per second squared and 1.31 newtons, respectively, while the actual values were 3.04 meters per second squared and 1.28 newtons, respectively. These values produce a percent difference of 7.04% for acceleration and 2.29% for tension. These values are within experimental error. The most likely reason that the values differ is that the theoretical values imply a frictionless, massless string and a frictionless, massless pulley, which are not reality.
That's sick, but why?
Background. The equations used for the calculations and experiment were only one. The net force equals mass times acceleration, which is also Newton's second law. The connections to Newton's first law of motion, which is that uniform motion is the natural state of an object, essentially saying that an object with no net force acting on it will either remain at rest if it's already at rest, or travel in a straight line constant velocity motion if it's already in motion. The Atwood machine that was built connects to Newton's first law, as the masses are going to move at a constant positive velocity acceleration throughout the entire motion, as net force does not equal 0, connecting to Newton's first law. The experiment also connects to Newton's second law, which tells us that net force equals mass times acceleration, as that's the major equation that we're going to use for most of the calculations. The Atwood machine has masses that move in opposite directions, so the net force equals mass times acceleration is important in finding the system's acceleration. Lastly is Newton's third law, which explains that every force is a member of an action-reaction pair, acting on two different objects and pointing in equal magnitudes in opposite directions. Although often said as, for each action there is an equal and opposite reaction, that really leaves out the important part that the action-reaction pair acts on two different objects. This experiment relates to Newton's third law of motion, as the tensional force on the string is in the opposite direction of the weight of the object. This can also be seen as the two masses are going to move in opposite directions, one going up and the other going down, and they're also going to go in equal distances, equal magnitudes. Based on all of the background and equations, a hypothesis was constructed, as based on the knowledge of Newton's laws and the theoretical calculations of acceleration and tension, the system's acceleration will be 3.27 meters per second squared, and the tension of the string will be 1.31 newtons.
Sick. Let me see how the shizzle works, you feel?
Nah, bruh. You first got to know how it's built.
Okay, to experimentally find the acceleration and tension of the system, we first need to set up the Atwood machine using the ring stand and pulley by securing the base of the ring stand at the edge of a solid level table using the big C-clamp. Next, we need to secure the pulley on the ring stand about 75 centimeters above the height of the table. Make sure that it is secure and level, of course. Next, tie the weight of each mass to the fishing line, and place the fishing line and weight system on the pulley, being sure to hold it in place so that it does not move, because if you let go, it will probably go flying. Next, tape the two meter sticks together side by side and place them vertically behind the Atwood machine, so that when you're looking at the Atwood machine through the video recorder, you can see the displacement of the two blocks using the meter sticks. Next, take a video of the motion of the weights on the Atwood machines by holding them so that their vertical positions start equal to each other, and then release them to record their natural motion. Repeat this step about at least 5 times and record data. Using the videos captured of each trial in the slow motion, record data for the displacement in a given time interval of each trial. After calculating the theoretical values of tension and acceleration using our Newton's formulas, calculate the actual values of tension and acceleration using the experiment data. Lastly, find the percent difference between the theoretical and actual values of both tension and acceleration.
Oh, no way. I'm really feeling them.
Yeah, you're feeling it. Check out these calculations.
So for our theoretical calculations of T and A, we first have our experimental setup of the Atwood's machine, with the 0.1 kilogram mass on the left and the 0.2 kilogram mass on the right, and we have the associated free body diagrams showing the forces of tension and mass times gravity. Then we can set up a two-system equation like this with the two different free body diagrams, and plugging in the known values, we can come up with this sum for the system, which gives us our acceleration of 3.27 meters per second squared theoretically. And then with this, we can use one of our equations to find the tension of the string, which would be 1.31 newtons. Then we can move on to the actual calculations that we got from our experiment, as each of the masses traveled 0.5652 meters in a time period of 0.61 seconds on average. Using our kinematics equation, we can find that the acceleration of the system was 3.04 meters per second squared, and thus the percent error can also be calculated as 7.04% error.
Man, I'm learning a lot today.
We're just getting started. Here's our analysis. It's mad tight, bro.
The raw data gathered in this lab was that the acceleration was 3.04 meters per second squared for the actual Atwood's machine, whereas the theoretical was 3.27 meters per second squared. The tension had an actual value of 1.28 newtons, with the theoretical value being 1.31 newtons. The theoretical calculations are shown below. To find the tension and the acceleration, Newton's second law, sigma F equals ma, was used, and it was rewritten so that tension equals m1g minus m1a, and tension equals m2a plus m2g, where m1 is the heavier weight, the 0.2 kilogram one, and the m2 is the 0.1 kilogram weight. Then the equations were set equal to each other, and the value of a was solved in terms of g, m1, and m2. Then the values were plugged in, and the acceleration was found to be 3.27 meters per second squared. To find the tension, the equation T equals m2a plus m2g, which was already derived earlier, was used, and the values were again plugged in to get 1.31 newtons. To find percent difference, the equation used was the absolute value of the theoretical calculation minus the actual calculation over the theoretical calculation times 100. The values for both tension and acceleration were plugged in individually. The percent difference for acceleration was found to be 7.04%, and the percent difference for tension was found to be 2.29%. There are discrepancies between the theoretical and the actual acceleration and tension, as shown by the percent difference, but these are within experimental error. One trend that's observable here is that both the actual acceleration and tension are less than the theoretical values, which suggests that there are other forces involved, such as friction. The theoretical calculations assume a frictionless pulley and a frictionless string, which are not reality, and these could lead to the percent difference.
Alright, time to wrap this up. I gotta get out of here.
Alright, 6 piece, bro. Catch you on the floor, homie.